Okay, chemistry time. Soon there will be, Fiat Lux, let there be light. Today, as you can see, we have a guest speaker. Wait, let me put it back to this view. This is William Eyelash, in the flesh, in the paper. It is not. This is not really William Eyelash. This is a poster of William Eyelash. Now, chemistry time. We are going to talk today about stoichiometry. I'm going to use a color that matches the color scheme. Stoichiometry. The word comes from, you already know what I'm going to do. What's the word come from? Greek, the Greek, that's correct. That's not what I was asking, but that is correct. You remember from your vocab? Comes from the Greek stoichios. And metros. That should be a little curly.
Is that autoklos?
No, it's stoichios and metros. Oh, I can't.
Is it an S, stoichios?
There we go. Stoichios, meaning, stoichios, meaning, do you remember from your vocab? I feel like I'm talking to hear my head rattle. What's stoichios mean in the Greek? Surely you know what metros means. It is the same root word as metric. What does that mean if I have, exactly, a measurement. So we got that one. Measurement. Stoichios meaning of an element. And this used fairly loose. I would guess that this word is in modern Greek used for these elements, but in the ancient Greek, and probably where this word derives from, I don't know this for sure, but probably where this word derives from, I would say initially referred to just the smallest part of something. Earth, wind, air, and fire, maybe even. But together, it means we're measuring the elements of something. And the reason I point out that it's just the smallest amount of something is that this is not always, what we think of as chemical elements is not always what we're, so to speak, measuring when we do stoichiometry. But now let's do, because we've already done one, let's do an example stoichiometry problem as kind of like my uncle taught my cousin how to swim when she was 2 by throwing her in the pool, and then she had to swim. I think he was drunk at the time, but because a reasonable person wouldn't do that, but she did swim, and she's been swimming ever since. And so in the same kind of way, we're going to just do a stoichiometry problem as the first thing. What? As the second thing now that, what? Yeah, everyone who has ever swum has either stopped or will stop swimming. Great philosophical point. Nothing lasts forever, Swanee. I'm glad you brought that up. Let's pretend we have, give me a chemical reaction. What's a cool chemical reaction? Or it doesn't even have to be cool. Give me an example of a chemical reaction. No, not the same one we did. Thank you. I mean, not the one from your lab. Let's give another chemical reaction. Can you think of one?
H2 plus O2 yields H2O.
I love that one. That's an excellent example. H2 plus O2 yields H2O. And let's say the question is, and this might be even in word problem form, it might say hydrogen and oxygen combined to form water. It might even say something like 63.9 grams of hydrogen combines with an excess of oxygen to form water. And then it might say how much water is produced in grams. That's a stoichiometry problem. The reason it's a stoichiometry problem and not a problem like we did from chapter 10 is that not only are we going to have to convert from grams to moles, but we are converting from one substance, hydrogen gas, to another substance, water. And that's stoichiometry. That's what it is to measure, convert, the elements, the different chemical compounds that make up a reaction. That's exactly right. The first step, and sometimes I have in the past written down the steps over here. If that helps you, you can do it on your own, but I will just say them aloud. The first step for any stoichiometry problem is balance it. When I say first step, if you aren't given the actual chemical equation, like if you're not given the skeleton equation, maybe like I said, the word problem is in words. Like maybe it is the words 63.9 grams of hydrogen gas combined with an excess of oxygen gas to form water. How much water is made in grams? If that's all in words, the first step would be write the skeleton equation. What skills do you have to do to write the skeleton equation from words?
You just have to know how many.
No, not quite. What do you have to do that you hopefully learned when you were in physical science, but definitely either revisited or learned this year, to get from words to skeleton equation like this. Remember? We had to know the names and formulas. You have to know how to find names and formulas. So you can do that. That's from, if you remember correctly, chapters 7 and 8. We're using 7 and 8 to get from words to formulas or back. We're using 9 to balance this. That's the first step. That's what I was going to say. The first thing we need to do is balance it unless it's not given. And that's from chapter 9. And then from then on, chapter 10. So really, the whole, basically what we've been doing since October or November has been leading up to this. It's cumulative. Not that I have designed a cumulative test that you have to know everything you learned all year, but the very nature of these problems is that they're cumulative. You have to know everything about chemistry in order to do this correctly. Everything. I mean, you have to know that all the categories of things that you have learned this year in order to do this correctly. So, we need to balance this. Let's balance it.
Put a 2 in front of the H2O.
2 in front of the H2O, which will balance the oxygens, and then 2 in front of hydrogens to balance the hydrogens. That is correct. Now, we start with our given. It's a unit conversion. 63, this doesn't show up super well, I'm going to switch back to blue. 63.9, this is where I'm going to insist, I told you about this in the last chapter, now I'm going to insist you must put the compound's formula with every unit. Why might that be super important here?
Because it's the measurement of each element.
Yeah, it's stoichiometry, which means we must, by definition, be converting from one element to another. And since we have this element in grams and we're trying to find this substance in grams, we're going to have to keep the grams straight. And by that I mean we have to keep which gram goes with which substance. So 63.9 grams of hydrogen. I'm going to set up my conversion bar. Next, how do I know what to do here?
You have to multiply the top one by 2.
Grams to
How do we know? Hi, Miss Neal. How do we know to convert from grams to moles? You just made that up and you are right, but you just happen to be right?
There's Avogadro's number.
No, not this time. These, without even knowing it, when we were doing this in chapter 9, these are moles. What you have done here is provided what's called a mole ratio. Meaning if we had 2 moles of hydrogen and 1 mole of oxygen, they would combine to form 2 moles of water. That's what these always mean. That's what the substance is. And you can take that as far as you want. If you had 4 moles of hydrogen, how many moles of oxygen would you need to make 4 moles of water? 2. It's just that this tells you the ratio. So you're already using moles. So we need to convert from grams of hydrogen to moles of hydrogen. I'll tell you too in a slightly better and easier way to remember in a second here now that we've gone through the theory. But now we're currently in, that is the unit we've converted to is moles of hydrogen. What do I need to convert now? Moles of hydrogen to moles of water. This, I always highlight. I put a heart around it. This is, as far as I know, I made this little notation up with the heart. This is not, if you do this in college, maybe your chemistry professor will think it's cool. Maybe they'll think you're an absolute moron. I find that this really, really helps students. Every single one of these problems will have a heart. And the heart is the actual mole ratio that is the stoichiometry problem. It's the part where you convert from one thing to another thing. And this can only be done if you're in moles, if you've already converted 2 moles. So the general form, if we were writing steps, balance the chemical equation, convert the first thing to moles, would be step 2. Whatever it was in, what if it was already in moles? Well, then you don't need to do that one. But convert the first thing to moles, it would be step 2. Use the mole ratio to get from one substance to another substance would be step 3. And then, what would my next step be? Am I done here? No? Now, exactly, moles of water to grams of water. And we always convert to grams? Why would we convert to grams in this case? Because it told us we're trying to find how many grams of water. The problem specifically said that, so we need to go that. And hey, why did your boy do all this without numbers? You should know this. And because I'm right, because this is the better way to do it. Set everything up with units first, and then put the numbers in. The numbers will just confuse you otherwise.
Yes, so now.
So the first step, balance the chemical equation. Second step, convert the first thing to moles. Third step, use the mole ratio to convert from one thing to another thing. Whatever number I'm on now, step, convert from if you have to, convert from moles of one thing back to grams or atoms or whatever of the last thing, and then you're done.
Would it be 1 mole over 1.00795
No.
grams of
Why? No
Because
and
you
why?
multiply by 2.
Yeah, so we have to show that work. You have to show this work every single time. So show this. You've done this before, yes? Yes?
Yes.
I think that's right. I think that's right. And if these aren't perfect, they'll only be imperfect to the extent that it is in the 10,000ths place, so we don't need to worry about it too much. So now, you would do that part in your calculator, obviously. You do need to show these steps, and that means in 1 mole of hydrogen gas, there are 2.0158 grams. Remember, this unit, grams per mole, means that in every this many grams, there is 1 mole. It's the same thing as over 1 mole. And we do that with the hydrogen because that's what our unit, consider this part of your unit. You just have to show that every time. What goes here? We talked about this yesterday. How do I find the mole ratio? What's this one? Y'all are both pointing and muttering, but I don't know what you're trying to tell me. I do know the answer. Where are these numbers going to come from?
The 18.
No. That's where this one will go. They're the coefficients. They're the coefficients. So 2 is with the water, so we put that on the same line as the water, and 2 is with the hydrogen. By the way, we didn't use it, but by the way, if it was this one, what would we put? 0? 1. Always 1. If you put a 0 on the bottom, you've made a black hole and you've destroyed the universe. If you put a 0 on top, no matter what you do, the answer will be 0. So it's never that. It's never 0. This number is implied to be 1. And then this one, Tiana, 1 mole is 18.0156. In this case, this is a wash, right? 2 over 2 is just 1. This is useless, but we still have to show it. It's mathematically useless, I should say, but we still have to show it because it's not always going to be that way. And then we get a final answer of, I'm going to put it up here. So what we would type in our calculator is 63.9 divided by 2.0158, enter. We can leave this out if we want. You could multiply by 2 and then divide by 2, but just don't do anything on the calculator with this, times 18.0156, enter, equals.
Wait, Mr. Crime, if you were to
Go on.
left hydrogen 2 as 1.0079, and then you would multiply by that 2, then that should be.
Yeah, but you can't do that because this is not just H. It's H2. It has to be because that's a diatomic molecule. You're right, but effectively your question is, 1 times 3 is 3, but if we made that first 3 at 2, then it would be 6. You're still right. That's not how the problem works. That's not what you were asked to do. What is the answer? Is anyone going to math it? Where are your calculators, dog? Okay, we'll just have to trust Swanee then. For the record, Swanee is muttering the calculations right now, just so you won't be able to hear that on the video. But what's the answer, Swanee? You want me to come hear that? Let me. Say it.
171.
That can't be right, can it?
Yeah, I figured.
Yeah, that can't be right. Let's try again. I don't think it's gonna be 3.5. Yeah, he didn't put parentheses on the top. Let me see if I can do 63.9 times 8. My marker is really getting in the way here. Think 0.0156 enter divided by, oh, he might be right. I'm so sorry, Swanee. I think this is right. I keep pressing the wrong button. You are owed an apology. That did work. 571. 571, that's with sig figs, 571 grams of water. No, it's because of sig figs. That little bit there was me closing the marker right next to the microphone because I was holding both. Yeah, so 571 grams of water. And now, like I just did wrongly, the last step, I think it's what were you on 5 or 6, is check for reasonability. Does it make sense that if we have 63.9 grams of hydrogen, that would make 571 grams of water?
Yes.
The answer is yes, because water has so much, is more massive per mole than hydrogen, and we would have had to combine with some oxygen. Probably a lot more oxygen. I do believe that that is it, except for vocab, which you should know on your own, and percent yield, which we calculated in your lab. Let me just make it clear to you. For percent yield, I'll just put this as a little side note over here. Percent yield is always the actual amount produced over the theoretical. It doesn't matter if it's in grams or moles or pounds or shoelaces. It doesn't make any difference what the units are as long as they're the same, times 100%. This is very similar to like when you take a test and you actually get 60 right out of 75. To find your percentage score, you could take 60 divided by 75 and multiply it by 100. So that's the percent yield. And then the other last thing, this is vocab, but I'll just tell you, is limiting and excess reagents. You'll notice that when I was saying this problem out loud, as if it were a story problem, I said in an excess of oxygen gas. And that's because an excess means that there's more than enough for this amount to fully react. In every stoichiometry problem, in reality, there's going to be a limiting and an excess reactant. There's a pretty good example of a basic elementary school version of that on page 379 here, where a person is building tool sets, and each tool set needs to have a hammer, 2 screwdrivers, and a pair of pliers, and they have all those things on top. How many tool sets can they make? Well, they can only, since there are only 4 hammers, they can only make 4 tool sets because each tool set needs a hammer. In the same way, if we said we had 63.9 grams of hydrogen and 63.9 grams of oxygen, well, one of them would run out first. And since that's the way everything is in nature, something's always going to run out first. That thing that runs out first is called the limiting reactant, as you found in your vocab, right? So the thing that runs out first as the reaction goes forward is the limiting reactant. Another example of this is from the same comic strip that made that one about Kerbal Space Program. He has one where he says, regarding making nachos, every nacho has a certain amount of chips and a certain amount of cheese, and as you make more and more nachos, either the cheese will run out first or the nachos will run out first. And that's not very funny. The comic itself is actually funny. I'm just paraphrasing it. But by the way, the math that you would do with that is that you would do this process for both givens. Like if I did say we also had 63.9 grams of oxygen, we would do this same problem for both, except for in one we'd have hydrogen, the other one we'd start with oxygen. And then with that, whichever one returns the lower amount, that's the actual amount that was made. In this case, it would definitely be the oxygen that would return the lower amount, and that amount is the amount that was actually made. And then it'll say which one was the limiting reactant. It's the one that made the lower amount. And we will do examples of that. I think that's it. Oh, sorry to jump back and forth, but where would the actual come from? I mean, where would you get a number for this? Of what? Well, so this would be the theoretical. The one you do the math for is the theoretical. Yeah, like if you're actually doing a real lab in real life, or in your book it'll say something like Sanjay Gupta makes 40 grams of water from this reaction. What is his percent yield? Well, you divide 40 grams by however much you got in the real math. That would give it to you. I think we're good though. And this is technically what I consider the end of Chem 1 curriculum. Like if you can do this, you have successfully completed Chem 1 because it takes so many of the things that you've already learned Since there's still more time in the year, we'll probably move on to some Chems 2 stuff for when you take that, which will include the gas laws, but we already did those in physical science too, but we do usually start with the gas laws. Do you have questions about stoichiometry? He's stoic about it,